Heavily requested item is a full rundown on Trane Cvhf, Cvhe series centrifugals. So we're going to put some time in and we're going to start talking about the various components and some of the basic operations of this without going too crazy deep into it, because I cover it in a bunch of different content. But I want to get you a basic understanding of what the components are and what they're doing and what the system uses them for. Starting here at the main controls. So this is the adaptive control. This is the older series. They do have a newer one. This particular controller will still work with the TechView series service tool. The newer one that actually has a graphical display and color and whole 9 yards will not. It requires the Tracer TU software. So this particular controller has a serial port here at the bottom. It's got a little flapper you can open as a protection. So that is that's where you would connect to it. If you had the newer one, it's got a serial port for this, like I think it's a USB-B style cable that you would see on like a printer, and you could either plug in through the side of the display. It's got a port here on the side of the panel you can plug in, or when you open the panel, they'll have a TU controller right here, little automation looking controller you can plug into. So that's for the newer equipment. This is the older series, but everything else is going to be almost identical. It's going to have a real basic rundown on the main menu. You have auto and stop here on the front. You can either go down item by item with the single arrow, or if you hit the double arrow, you'll jump a whole menu set at a time. Whenever this chiller is running, if you hit stop, it's going to go into a cycle down stop. If you hit after you hit stop, it's going to ask you hit stop again or click. There's a separate button for immediate shutdown. And when you hit that, you only want to do that in an emergency if you have to. But when you hit that immediate stop, this chiller is done. It completely halts in its tracks. It's really not good for it to do that either. So I highly recommend you use that sparingly. From there, you're just going to go into the report section. I won't go through all these right now. I can do another video on just these though, and go through this whole controls. In the meantime, this gives you all your different reports that the system is getting back. And then if you need to make changes to those reports, you could come over here to the settings and you can actually make your changes that you need to, your manual control, turn your oil pump on, whatever you have that you want to do. So that's the adaptive view control itself. From here you go into the main control panel. All of this on this particular series is done via a COM bus, and so all these are little COM cards that all connect together and communicate back to the main controls. If one of these goes out, usually it will identify it to you. I've had these fail where the relays or something go out and that particular component won't fire, or I had one where the sensor it was one of these style boards, the sensor circuit did not pick up properly, and I was having a sensor come in to confirm that we were closing our flow switch, but it was not registering that because the board had failed. These boards have to be binded just like you would do any other sensors on this chiller. Now if you're working on a much older series, before they had the adaptive view controls, you would have the standard the 1U1 or the 1U control modules that would run all the sensors and everything would be wired. Once you step into this adaptive control, everything goes to a ComLink bus, and you have to have TechView in order to control it. The other series that did not use the ComLink did not require adaptive, tech view, you could just, everything was hardwired, or you controlled it through the control panel. Again, these are just all your various relays. This is your basic controls for the chiller from right here. From here, they bleed over to the main power cabinet. So, those are your motor terminal lugs up top there. Your main power lugs coming in. There's another relay COM board there. So this is your control cabinet. I will do a quick shot of it here. So up top there, you've got the resistors that help with the starting circuit. And this is a Y delta start sequence. And so this is your primary, your secondary, or your run, and then your start contact. So what you'll see happen is it will, if I remember correctly, the pattern is it hits the primary, releases, hits the start, and then the primary hits and holds, and then the start releases and the secondary engages. And anyway, it cycles through that process. At the end of it, once it's started, these two here will be the two that are constantly on throughout operation. The point of that whole start sequence is to get some pre-rotation on the chiller motor, so that it will make it less inrush current at startup. So that's the primary function there, and the goal behind doing it that way. You do definitely need to make sure you maintain the contacts, the coils, everything on those very, very well. Okay, so we're going to move on from the controls cabinet, and we're going to get into the meat of the rest of the chiller. End of the day, this is your evaporator. That's your condenser back there. This is just a standard setup. We do not have any kind of heat recovery or an auxiliary condenser or anything fancy like that. You've got your suction pipe coming up into the compressor. This is a Cvhf compressor, which means it only has 2 stages. A Cvhe will have a 3rd stage in between. These Tranes, both series, use 2 guide vanes. This is a traditional style guide vane with actual veins that it goes through, a paddle type vane, and these are a little bit different style. Trying to think how to explain these. This is more of like a it's a rotor type style vane. I'll try to add some footage from a recent teardown we did on those. Anyway, these vanes, their purpose is to load control, and so the refrigerant's going to come up through the suction, and it's going to hit that vane first. So at startup, these vanes have to be at full closed. If they're not, this chiller is not going to start up without tripping on inrush current or something of that nature. You cannot, and you do not want a load on this motor at startup because it requires so much starting current. So it is looking to these to fully close, which it has a actuator arm here that opens and closes it. This older series does have a communicating module that runs that arm. This arm will routinely go through a calibration at startup, and so that's one of the things you can expect as part of the process. You'll see it extend all the way out and come back in. You definitely want to make sure that all your joints and ligaments are properly tightened down and everything is moving freely. You do not want anything on these arms to bind, and these arms do swing together in unison. Now, if this was a Cvhe, this is your first stage, your second stage impellers right here at these joints. If this was a Cvhe, you would have a third joint right here that would not be insulated. This insulated joint would be a little further over, and between those, the first and second stage, there would not be a guide vane. This guide vane would still be on the third and final stage impeller. The way the chiller is operating overall is, once it starts up, it loads the chiller by opening the vanes, and it's paying attention to the chill water leaving. So if set point is 45, when we hit 45 degrees of leaving water, it's going to slowly start unloading the chiller and closing the vanes in order to keep the load down so that we don't overcool the loop and get too far below set point. Now once it unloads to its maximum ability, it will just maintain that until it can't keep the set point or the leaving water up above set point, which at that point it just cycles off on load, just like any other regular air conditioning system would do. When the thermostat satisfies, it turns off. Well, the chiller will do the same thing. Now most of the time, and the goal for this is we don't ever want to have this chiller turn off at all, or especially any more than it absolutely has to. You want this chiller to stay online for as long as possible, as much as possible. So just keep that in mind, as we don't intentionally want to set it up or put parameters in place where it's constantly turning off and on. It's a lot of extra stress for the chiller, and you lose a ton of efficiency in that process. Anyway, guide vanes allow very strong loading and unloading control. Other brands like York do use the guide vanes in the same way. All centrifugals will use the guide vanes in the same way for loading and unloading, but when it comes to when they start dealing with surge and various things, exactly how they end up closing them and to what extent is where they may differ a little bit. But at the end of the day, all centrifugals are going to have the same basic principle on the guide vanes. From there, we can move on to the condenser and economizer sides, the next place to start. So we go through the suction, through the impellers, and then we come into the volutes and out of the scroll. So this is called the scroll or the volute, and it comes down into the condenser. And so from the condenser water is going to remove the heat, send it out to the cooling towers or however you decide to utilize it, and it's going to function as a standard condenser at that point. Coming out of the condenser, you've got your liquid line, which is right here. So your liquid line comes out. I'm sorry, this is a little dark. I should have grabbed my light. Liquid line comes out, and then it hits the very first flash plate. So that flash plate is where we go from the liquid line to the two-phase line and up into the economizer. So you're going to pull through the liquid line. You go through a flange, which inside that flange, again, there is a flash plate there. And that flash plate is just a perforated plate that the refrigerant flows through to flash it, just like it would do through an orifice. It's going to come up into the economizer. It's going to go through the economizer, back out the bottom, and it's going to go up under into the evaporator on the back side and through another flange and flash plate there at the evaporator. So what's happening here is this economizer is allowing for flash gas to collect in the top. So, leaving a TXV, we have to flash some of the refrigerant in order to start creating cooling, because we have such a great pressure drop and we have a larger opening that we have to fill the void inside the space of the pipe. That's basic theory on a TXV. Well, we kind of have the same principle here. Is, say it's a 2080 mixture or 2575, depending on who you talk to. Well, that extra 25 or 20% of flash gas that flashes off gets collected here at the top of the economizer, and all the liquid refrigerant stays there at the bottom. And what that does is that takes all the extra heat content that refrigerant flashed off. That's how we get the flash gas. Is we flash the heat that's out of the liquid line that's already subcooled, and subcool it even further by flashing it. So we could turn that, just an example, we could turn that 8 to 10 degree liquid line subcool into a 15-20 degree subcool by the time after we come out of the economizer. And we do that by using the economizer itself. And this line here is the flash gas suction off of the economizer, pulling back into the second stage impeller. Or if this was a Cvhe, you'd have two pipes coming off into the second and third stage impellers. Ended up getting some light to put on the situation. So this is our liquid line, so two-phase line. That's our flange with the flash plate. We come up here to the economizer, and there's the flange going into the evaporator. Now, a big difference between the Cvhe and F, again, like I said earlier, you got the two pipes coming out for the E, but the E also has another plate in the economizer. So the Cvhf only flashes twice. The Cvhe will flash 3 times. So it'll do an initial flash off the liquid, come up, flash as it's going through the economizer, and then the final flash will be as it's going into the evaporator. And then from there we go back into the evaporator, up through the suction, take the heat out of the water on the chill water, bring it through the compressor, put it back in the condenser, take it back out through the condenser water. That's all it is. And that's all these chillers are. We're just taking the heat that's in the chill water, which is getting collected from the building, and we're putting it in a different water loop, which would be the condenser water, and rejecting it somewhere else where we can either utilize it in some other way, such as heat, or just completely discharge it outside to the air where it doesn't matter. The next item on the ticket is going to be our Purge Assembly, since we're here. So the Purge Unit's main function is to just purge any atmosphere out of the system. So what it's doing is you have condenser gas coming up, and it is naturally going to come to the top of this reservoir tank. So this is actually a heat exchanger, and what we're doing is the condenser gas comes in and comes into the top of the tank, and there is a little coil inside of here that this compressor is cooling down. And as that compressor cools that coil, the refrigerant condenses at a higher temperature. The refrigerant condenses at a higher temperature than atmosphere does, or moisture or anything else in the system. So the refrigerant condenses and then comes down out of the tank, and gravity feeds back through this filter and drains back into the bottom of the condenser. And because this is a gravity feed back out, it naturally pulls a siphon and pulls more refrigerant gas back into the tank. So it's just a natural siphoning effect. And that's all it is. So what happens though is we're monitoring this suction temp, and when we lose superheat completely and we get down to say 18, 23 degrees or below, typically, you will see this, you'll see our purge go into a pump out. And so what's happening is the atmosphere is collecting up here at the top of the tank, and as it increases how much atmosphere is inside the tank, we lose how much load is on that coil, because as long as there's refrigerant in there, there's load on the coil. When the refrigerant level is down really low because the top of it is full of atmosphere that's getting trapped, then we don't have much load on the coil, meaning there's a lot of atmosphere and not enough refrigerant condensing, and that's going to give us a really low superheat, which is in turn going to tell us, okay, we need to go ahead and do a pump out, which at that point our pump out pump turns on. We do have some isolation valves for protection, and it's going to go through and reject that atmosphere out of that tank. Now, after it comes out of that tank, it then comes over and goes into this Regen Tank or reclaim tank, however you want to look at it. Not all models have this. Most of your newer ones do. What this tank does is it's got I think it's a carbon type filter in there where it actually collects the little bit of refrigerant molecules that get discharged with the atmosphere. So you will lose a very small amount of refrigerant from the system just through the pump out process. This Regen tank's job is to collect that refrigerant through a filter, and those molecules bond to it, and the atmosphere is allowed to pass through with a minimum amount of refrigerant possible. So every so often this tank has to go through a burnout process, or I forget the exact term the factory uses off the top of my head. Anyway, what it does is it doesn't pump out like it would traditionally. What it's trying to do at that point is it heats that filter in there up with an element to, I think it's 120 degrees or 140, something like that. Heats it up, heats that element up hot enough to where the refrigerant molecules unbind and flow out back through into the chiller and can be put back into the system. And so we're on systems that don't have that, you'll only have one pump out solenoid over here, but on these particular systems that have that recovery ability, you'll have a second solenoid, and its specific task is for the reclaim cycle whenever that tank heats up, and it's allowing that refrigerant to go back into the evaporator. And so that's what it's doing, is as it heats up, that evaporator pulls that refrigerant back in. So that's your purge unit. That's its basic function. This particular one does communicate with the main controls. Again, some of the older ones, or if you get a older chiller that you put replace the pump with a newer one, or the purge assembly with a newer assembly, it may have its own little control panel here where you can take and set parameters because of the old controls that are in the system. Anyway, that is your purge function. We've covered the basic guide vane functions. This here, sticking out of the suction elbow, this is your burst plate. Most of those are set on this, so this is a 123 machine. All your low pressure machines will have a burst plate in them, and they're usually set for 15 psi. So when that evaporator suction gets up to 15 psi, which when you're pressure testing and things is really easy to do if you're not paying attention, you'll overpressurize it and burst that plate, and you're talking anywhere from $500 to $1,000 to fix that, depending on which manufacturer you're working on. From there, we will move on. Next, we come over here to the water inlets and outlets. So, the most critical temperatures on these is especially going to be your leaving waters. So, this chiller will not run properly. It won't do hardly a thing like it's supposed to without the chilled leaving water temperature sensor reading correctly. And again, these are network binded sensors, so you have to go through the binding process, which again I have a video for online. But it's just taking these readings and this is how it's going to use its staging. So depending on how far above or below set point we are, depends on what the guide vanes do to modulate to try to control set point. Then you have your condenser water temperatures, and depending on your area and where you're set up will depend on how you can maintain and control those temps. But typically, you know, the lower the temp you can maintain within reason, the better. Usually on these Cvhes and Fs, I like to try to run like a 70-degree water. Sometimes I'll let it go down to 65, but I find in my personal experience and the way most of my plants are set up, they do better at 70 degrees. Now it's different for other manufacturers. For like a York, for example, a YK and a YT, I see better results on about 65 degrees efficiency wise, 60 to 65. So they actually do really well at those lower condensing temps. This thing just turned on, so it may get a little noisy for a few minutes. But you can see, so the guide vane here is slightly opening very, very slowly. Now it's going to run at a minimum load for several minutes as it goes through a startup procedure. And here's something I want to warn you guys about. This pressure right here on the evaporator, let me get in there, and on the condenser, those pressures are not actual transducer pressures. Those pressures are conversions through temperature sensors. So this is your Evap temperature sensor, and around here let me get to it, and you can't see it now, but up under here on this particular series, the in the liquid line is your condensing or condenser refrigerant temperature. And then it takes that temperature and it's converting it into a pressure. And so a lot of times, especially when you start seeing surging, you won't see readings here on the display that indicate, well, why is it surging? That doesn't make any sense. That's because if you actually put a pressure gauge on it, you will find that the actual pressure is very different than what the display is telling you. That is because it's not running at a stable operation, and that temperature sensor cannot fluctuate like the pressure is fluctuating. So you have to take that into account when you start doing heavy troubleshooting, especially with things like surging. You can't trust those numbers completely. You're going to have to put your own gauges on it to get your own baseline as to what's actually happening live in the system. The only transducers this thing uses is like on the oil pressure is an actual transducer, but the refrigerant pressures are not. They are strictly conversions of a temperature. and those need to be very, very accurate. So when I do annuals on these, I will take and do a, I'll put my gauge on it and I'll compare my gauge saturation to the temperature saturation of the refrigerant. And if they're more than, say, a degree or two, maybe 2 degrees off, if they're more than 2 degrees, I'm replacing them because I'm losing efficiency. And it could cause other problems in the system long term. Here you have the oil sump assembly. So inside of this oil sump, you've got a motor and a heater. That purpose is to, the heater keeps the oil temperature up to above 120, and I believe it cuts out at 140. So 120 to 140 is the optimum temperature range for the oil. Typically the oil heater will only run when the chiller is off and is trying to maintain a 120 minimum. And then once the chiller turns on and gets online, usually the motor and the operation will have enough heat generated to keep the oil temperature up. And that's because we need to keep it at a very specific viscosity. Anything above or below that, we get too far outside of our viscosity range, which affects its ability to lubricate all the bearings properly. This chiller does have journal bearings, meaning that it does require heavy oil lubrication in order to protect the bearing, especially during regular operation. And so those journal bearings, they don't like to take, they require oil to help make that part of that seal on the journal. And so if you watch my teardown videos, you'll see where the oil injection port comes in on the compressor, and that is specifically for that journal bearing. Anyway, you have your oil temperature sensor and you have your oil sight glasses. I like to keep my sight glasses either between them, or I really prefer to be up into the upper sight glass. That is my preference. I like to maintain there to make sure we've got enough oil. If I get down into the lower sight glass, when I start seeing it there, I usually start recommending to the customer, we need to either see if we're losing oil, or if we're having a migration issue, or if what's going on, and then possibly adding oil if needed. This is your oil filter. You do have a filter adjustment there, so that this is for the run cycle. Whenever you go to change the filter, you have to drain it, and then you move this over to the change filter setting, and you can spin this canister filter off, spin a new one on really, really quick without having to take the whole machine down. This is your oil pressure regulator here on the side. So if you need to make any adjustments to your oil pressure, it's not regulating properly, that is where you can do that. This is a refrigerant pump for the machine. You also have your get in there, that little canister style filter there. That is going to a oil return line coming off the bottom of the evaporator, and so that comes off the bottom of the evaporator to help any oil that gets into the evaporator return back to the sump if ever needed. So these lines on top, these are all part of your sump return lines, where it's dumping back into the oil sump. And you do want your oil sump to be at a lower pressure than your evaporator. And so if you start to see that they get really close in pressure, or if they're equal, or if this is higher in pressure, there's something going on with the system, and you need to dive in a little deeper. This is the oil return line coming off of the motor bearing, and it's going to drain down into this little tank assembly, and this is a oil refrigerant separator. And so the goal of this is the oil will collect in the bottom of this reservoir, and the refrigerant will rise to the top, and then we'll pull back into the any gas or refrigerant that flashes out of the oil can then pull back into the evaporator, and so it doesn't get into the oil and collect and build up and then create problems because of oil or refrigerant in the oil. That port there on the bottom of the scroll housing there underneath the motor, that is the front bearings oil return line coming back as well. These here are your motor cooling lines, and so this is coming off of your refrigerant pump off that's down here off of the sump, and it's pumping the refrigerant in through a flash plate there into the motor to help cool it, and then it returns back into the condenser. Again, that's just to help keep the motor's temperature stable. These lines here are coming off of your motor, your oil sump pump, pumping up through into your oil inputs. So this is the motor rear input, and you've got another front input up there, and that is your oil pressure transducer there. So those are your basic components on a Cvhe, Cvhf series. Like I said, I was trying to do just a real basic rundown. There's a whole lot more to get into on these. I'll try to do some other subsequent videos to get a little deeper. For example, I'll try to set up time to do a full rundown on a adaptive controller and let you see all the ins and outs, all the different parameters, my recommendations, what I see from experience happen, and help give you a better picture as to how to better use that control and navigate it to control your equipment better. Anyway, I'm going to close this one out. I appreciate it, guys. Hope you enjoyed it, and hope this helps you.